Good day everyone. Today we will be presenting our assignment 2 for CST435, which is about parallel computing. First, let's look at what we have built. The core task here is a CPU-intensive pipeline that applies 5 distinct filters. These include grayscale, blur, edge detection, sharpening, and brightness. This pipeline will be applied to every image, and we tested this on different datasets which are 10, 100 and also 500 images. To optimize this, we implemented data parallelism using two Python approaches. First, multiprocessing. Multiprocessing is a process space where it utilizes multiprocessing pool to spawn separate operating system processes. It will bypasses the global interpreter lock by assigning independent memory space to each worker, and this is ideal for CPU-bound tasks. Next is Concurrent.futures, which is a thread-based. It will utilizes thread pool executor to manage threads within a single process. It will leverages OpenCV's internal GIL release to achieve concurrency, focus on efficient input-output management. For our experimental setup, we deployed everything on Google Cloud Platform using an E2 standard at virtual machine running on Ubuntu. The most critical detail here is the processor. Even though the system lists 8 vCPUs, it actually runs on just 4 physical cores. This hardware limit is exactly what we wanted to test. For the software, we use a standard Python environment with OpenCV for image processing and Matplotlib to generate our performance graphs.
For demonstration of running image processing of both MP and concurrent process on the VM, first we start the VM instance and open SSH on VM. So we already cloned the project file on GitHub to VM, and we go into the project file. So we have to activate the virtual environment first. And then if you see on the list of the files, we have create subset.py that creates subset from the image folder that we upload to the SSH. So we want to create different images in different subset. So make sure you remove the previous subset to create a new one. And then we also need to clear our output results so that the storage is enough to run all the image processing. So here we create subset of 10 images. And then we run the Python main.py to start the image processing for both MP and concurrent processes. Alright, so we get the results here. And then this will be repeated for a few times. So we need to repeat for subset of 100 and also subset of 500. Okay, 100 images is created. So the processing is for each of the process for each of the running of the image processes. The processing is run 3 times to get the mean for the speed of the time processing and its throughput. And the processing also includes running different numbers of workers, 1, 2, 4, and 8 to compare the performances of different number of workers for both of the paradigm. So lastly, this is the subset for 500 images. So we create a new subset, 500 images, and then test it for the last time. As you can see here, for 500, the timing is like significantly slower than 10 images and 100 images.
For our first test, which is with 10 images, threading was the clear winner. As you can see, It finished in 0.15 seconds compared to 0.17 seconds for multiprocessing. The reason here is simple. Initialization cost. The time it took to spawn disparate process, which is known as forking, was actually longer than the time it took to process the images. Threading had negligible startup overhead, making it faster for small tasks. When we increase the load to 100 images, tables turn. Multiprocessing took the lead at 0.37 seconds. Here, the workload was large enough to justify the startup cost. Because multiprocessing bypasses Python CIN log, it could fully utilize the raw calculation power of our 4 physical cores, processing the matrices faster than the threading models. Finally, at 500 images, threading won again, not because of raw speed, but because of stability. When multiprocessing had a lower median time, it was incredibly unstable with massive variance. This is because the system became input-output bound, trying to write 2,500 flies at once. This caused the multiprocessing workers to crash or trash resources. Threading, however, handled this perfectly by yielding execution while waiting for the disk, keeping the system stable. To wrap up our analysis, we identified 3 critical findings. First is hardware alignment. Our performance gains stopped increasing after 4 workers. This confirms that physical cores matter more than virtual CPUs. Once we exceeded our 4 physical cores, the system was just context switching, not truly parallelizing. Second is theoretical limits. Using Amdahl's law, we calculated that about 9% of our pipeline is strictly sequential, like reading the file list. This means no matter how many processes we add, we can never speed up the process more than 10 times. Finally, stability versus speed. While multiprocessing gave us the faster raw numbers, it crashed under heavy load. Threading was slightly slower but kept the system stable. For a real-world production pipeline, we would choose stability, which is threading, over raw speed. To conclude, our experiment proved that there is no single best parallel method. It depends entirely on the workload. We recommend multiprocessing if you need raw calculation speed for medium-sized tasks. However, we recommend threading for large-scale production. As we saw, it withstands heavy file input output without crashing.